Hello everyone, welcome back to Digi Structures. So let's dive into it. This is the part 2 of the shear stress and beams derivation. So now I would create a distinction. This is where we stopped. I'll be having phase A, phase B. Yes, phase A and phase B. So I remember force is equal to this times dA. So it means that in my phase A, my force will be equal to, since sigma was my over I, so my over I dA. While for this, the same times dA. So F is equal to m plus dm, a variation of the moment, y dA. So now you will see that this can never be equal to this. Had it been the moments were the same, which in turn means that the stresses were the same, the forces would have cancelled out. They would have cancelled out, which would mean that there won't be any tendency for what is the word? For slipping. No, slipping is not the word. For sliding, exactly. There won't be any tendency for sliding. But because the forces are different, it means that there will be a tendency for sliding. So let's calculate that amount of force that would want to slide the layers apart. Of course, the amount of force or the magnitude of force that would want to slide the layers apart will be the difference between this force and this force. So this is F2, F1. So that net force, F net, will be equal to m plus dm y over I dA minus my over I dA. After doing your simplifications, you'll be having, in fact, y dA over I is constant. So m plus dm minus m, F net. So it means that m cancels m, and it means that we're left with our unbalanced force, which is equals to y dA over I times dm. This is it, guys. So, but this is just for a single cylindrical bar. Remember, for the sake of simplicity, we're just dealing with a single bar. So, but if, okay, let me, F net is equals to y dm over I times dA. But if we are looking for the total force, it means that we need to find, see what I mean? It means that we need to find everything here for all, zooming in, for all of this enclosed area. We need to find everything for the cylinder. And the only thing, we need to assume that there are a lot of cylinders there. And the only way we can do that is for us to integrate. Oops. So this is just for single. Yeah, for us to now get the total area of the enclosed stuff, you have to integrate. So total force, total unbalanced force, will be equals to integral of y dm over I dA. So it means that our F total will be equals to dm over I y dA. But recall that when we did centroid, we said we did something like this: a1 y1 plus a2 y2, And we said that that's this particular expression, which is equals to this expression, must be equals to the same thing as this expression. So it means that I can substitute this expression using this expression. So for me to do that, I will say that my F total must be equals to my dm over I times my ay bar. Yes. But now, remember that force once again is equals to stress times area. I remember that this is our unbalanced force that needs to be balanced in order for slipping or sliding rather to be prevented. And for us to balance it, we have to equate something that is equal to this magnitude, to equate it. That is to prevent the sliding from happening. To prevent the sliding from happening. So, sorry for the noise disturbance, guys. Sorry. So it means that, remember, when I talk of, remember I was dealing with layers of the beams. Let me go back to this. Let me go back to this. Go back to this. So I'm just basically cutting the beam like this. That is what I'm doing. And if I cut it, it means that my distance from here to here is B. Let's say it's B. And my distance from here to here is dx. I remember that since we're dealing with the layers, it means that my area must be B times dx in that regard. So my area of the layer of the beam is B times dx. So area is equals to B times dx. So I can say that, or remember I said that we need something of the same magnitude to balance out this expression so that the sliding will not happen. So I can say that my resisting force rather, force must be equal to that same expression, because that is the only way it can cancel out, times ay bar. Exactly. And that resisting force would act along the layers. That's why I brought this layer out. And I showed you that, okay, to find this force, we need this stress times area. But this time, since we are dealing with, since that stress is the shear stress, it will be shear stress, which is tau, times B times dx, which denotes half resisting force, must be equal to dm over I times ay bar. Once again, this same expression is the same magnitude of the force that we want to slide the layers apart. But now, since I know this certain magnitude, I want to slide my layers apart. It means that once I equate something opposing this particular force in an opposite direction, but would have the same magnitude, it means that it will cancel out eventually, and it means that I won't have any sliding effect. So this particular force is called that shear force that will tend to resist, the sliding effect. And since it's shear, I'm dealing with tau now. That is why it's tau I'm dealing with, times B times dx. So I can now say that my shear is equal to dm over dx. I just times AY over I times 1 over B. Now, remember that when this is our shear force, for instance, and of course, our bending moment will be something like this. It will be a parabola or something, yeah. If this is a straight line, it just means that when you integrate your shear force, you have your bending moment. And when you differentiate your bending moment, you have your shear force. So it means that when you differentiate your bending moment here, I'll be having my shear force. So shear force times AY over B high. So basically, this expression basically means that this will be the amount of shear force that will want to cause a resistance, or rather this will be the shear stress correlating to the shear force that will want to resist our sliding effects caused in the beam due to a variation in the bending stresses. Thank you.